on the scaling. Okay, then this one, I did not teach well, right, before you do the assignment, but I gave you the answer. Basically, I just asked you to plot it. Right, so basically last time we say that first you learn from quantum mechanics, V equal to 0. And if you have an infinite potential well, your particle is not going to attain the minimum energy. This is the wave function, right? Yeah, Abdul, you have a question?
Yeah, so were we supposed to derive an expression for the classical threshold voltage versus silicon film thickness?
No, you only need to do that with the quantum mechanical one in the assignment.
Okay, got it.
Yeah.
But in this case, EC0 is the classical one, right?
EC0 is the classical one, and you don't know what it is. Yeah. Because
okay,
my goal is to ask you to find out what is EC minus EC0. This is the delta VTH, proportional to delta VTH.
Right. It's only pretty much it's pretty much VTH or EC divided by Q, right?
Yeah, if you want to get the number correct, yes, divided by Q. Yes. Okay. Now, in a classical potential well, we know they have different level, right? So we can call this, I put this E0, but this is not EC0. This is already a new energy, right? You cannot have energy in between. So similarly, when you have the silicon on insulator, when it's so thin, this is the EC0, right? This is the EC0. But your energy, just like this one, right? So maybe I should use another color. This is the EC0. Just like here, this is the ground energy. Classically, you can have V equal to 0 or energy equal to EC0. But quantum mechanically, because of the confinement, right, you are going to have, this is wave function, you are going to have this energy, E0. Okay? And here, you are going to have something. I should not write this. You are going to have a confinement like this. Okay? And this is the EC. Okay? So you have a new EC, a new energy. Okay? So as a result, you have a higher threshold voltage. And that's why when you go down, the quantum mechanically, it will go up. Okay? So this one, after all, I just want you to be familiar with the fact that, hey, you make it thinner, your threshold voltage is going to go up. This is something happened in FinFET also, right? So this is something you must know. But whether you know how to calculate it, I don't ask for that actually. Right? Exercise for assignment, I ask you to plot it so you have a feeling, right? But I don't expect you to memorize this equation. But you can Google, right? Any questions?
Professor, that EC, is that a conducting balance?
That EC what? Say again?
Is the EC directly connected or related to the balance, the conductance balance band?
They are all conduction band. So conduction band is the lowest energy. Conduction band edge is the lowest energy the electron can have, right? It's just like here, the lowest energy the particle can have. Now, due to confinement, its energy is actually a little bit higher, have this delta, and this is the new EC.
So in this quantum mechanical effect, does it affect or does the Fermi level disappear in the Venn diagram,
No,
or
Fermi level is still there.
okay?
Yeah, no, it does not. So basically, so quantum effect, basically, you can treat it as I have a larger band gap. Then that might be easier for you. So when you confine it, originally your silicon has 1.1 EV. Maybe now it become 1.1 plus whatever you get here, whatever you plot in the assignment. So band gap becomes larger. So the whole conduction band shift up. You can think in that way also. Right? So now for example, this particle can only have energy E0. Then I can say that, oh, just because my ground level is here, not here. Right? Is that okay?
Yes, Professor, thank you.
Okay, great. Now, so if you look at the ultra thin body, right, UTB, there are many abbreviations. Now, what happened when you look at the mobility, right? If we look at the thickness, when it is very thick, mobility is the same, right? But when you get lower and lower, you will get a bump. Mobility suddenly go up. Why? You probably don't know unless you learned this before. This is because it reduces the so-called intervalley scattering. So in silicon, we're going to cover a little bit later, but I think you learn about this also, right? Silicon, it has 6 values. If we look in the K space. Right? If you don't know what I'm talking about, it's also okay. You just take it for granted. Right? I won't test you, but you do need to know that if you want to discuss with people who are in the device. Basically, in the whole reciprocal space, right, momentum space, it can have lowest energy in this 6 value. Okay, so what is mobility? Mobility is related to the scattering, right? You knock on something and then you got slowed down. That's a very classical picture, right? But in addition to that, we can formulate it just like in the momentum space. We can say that it changed the momentum. So instead of saying that, okay, I run into you and then you knock me, then I go to the south by 30 degrees. That is one thing, but I also can say that I run to you with the momentum 1 unit of kx, then you bump me, and then I go to kx plus ky 45 degrees, right? That's the momentum, the same description, right, for scattering, right? So this is what it's describing. And how easy it can scatter depends on many mechanisms, and the physicists already summarized them. One of them is so-called intervalley scattering. So you can have a particle that is maybe in this space. Again, this is not the real space, this is the momentum space. And then you get scattered to this space, right? Because of quantum mechanics, it's not that you can go to any space you want. You need to conserve the momentum, you need to conserve the energy, and also you need to have the appropriate phonon. But it's very easy to understand also, right? If now we are in the classroom, I run into any one of you, and then you want to scatter me, right, to the door. I need to have certain condition. For example, I need to run in the right direction, right? If I run backward, you can never scatter me to the door. I need to run into you. And then you need to be strong enough. And not just strong enough, you need to throw me in the right direction. Then I scatter to the door, right? So anyway, the main point is there are many types of scattering. For example, in the classroom, maybe if we only have 5 people, I only have 5 different types of people scattering. Same for different geometry, different crystal, different condition. Certain scattering is important, right? For example, if all of you are very nice people, even I run to you, probably you only say sorry to me instead of scatter me to the door, right? So there's no scattering mechanism, right? So it turned out that intervalley scattering is something important, but when we make it very narrow, very narrow, this effect disappear. Why is that? This is because when you make it narrower, the quantum confinement effect is different for different valley. For example, originally, all these 6 valley have the same energy, right? But after you do the quantum confinement, because it breaks the symmetry, right? Because now I confine only in one direction, you may get 2 valley in here, right? And then another 4 valley here. So earlier I can scatter, because you have the same energy, I can scatter you between this energy, this valley. But now you lift what we call lifter 4 valley. I need extra energy to go to the valley. So as a result, I cannot go there. So the scattering mechanism disappears. And that's why the mobility goes up. But later the mobility goes down. Can you guess why when I make it very thin, the mobility is going to go down? Anyone want to guess? Basically what we are saying that when the oxide is like this, and then I have silicon here, and then you have electron here. When I make it very narrow, the mobility goes down. Yeah, someone. Yeah.
Smaller channel.
Smaller channel, right? But we're talking about mobility. So mobility, in principle, does not depend on the channel. You are right. I think you might referring to something, but what you are saying is not exactly. Say again.
I was thinking about velocity.
Less freedom.
Right. But you are talking about mobility. I want to continue on what you're saying. Let's say I have a 5-lane freeway. I drive the same car. I have certain mobility. Yeah, you have the velocity, but let's talk about mobility, right? The mobility is like this. If I make it 2 lanes or 3 lanes, the mobility is still the same, right? Do you think so? If I'm the only car, right? 5 lanes and 2 lanes are the same for me, even 1
Unless
lane.
there's traffic.
Right, we don't talk about traffic because now I only make it thinner. It doesn't mean that I have more traffic, because mobility is just talking is related to per unit. I mean, it's not about the current, amount of current. It's about under the electric field, how fast I can move, right? V equal to mobility times E. So mobility equals to V divided by E. Right? So E is the gas. You press the gas pedal, right? You have the force, and then you go in a certain velocity. For 5 lane and 1 lane, do you think you have the same mobility?
Yes.
Yes, right? So it should not get slower, right? Mobility should not become slower. But what can make you think about that? But
Lower,
I tell you it's lower.
To invert the electric field.
To invert the electric field, this is the electric field in the transport direction. We're just saying, given the same electric field, what velocity do you have, right? So yeah, you take higher voltage to invert, but once you reach that voltage and electric field, the mobility I still expect to be the same. Now why don't you really imagine for 5 lane, really imagine you're driving for 5 lane, you drive in the middle, probably you dare to run for 100 miles per hour, right? Now I keep squeezing it, and now you only have 1 lane. Do you dare still to run for 100 miles per hour?
It will remain the same, right?
You remain, but psychologically, are you there to run at the same speed? What if I make the lane even narrower?
No, I would not.
Okay, okay, you won't get a ticket. Actually, my analogy is not good, but can you tell me why you not?
Because you have a higher chance of running into the barriers.
Yes, because now, although you did not, but psychologically, you see there's a barrier next to it. You can crash easier, right? But here, of course, electron don't think in this way. Here is that when you are narrow, the electron has more scattering with the surface roughness of the interface. The interface is not really perfect. When you make it narrow, electron will scatter more, right? Because now it's closer. Your electron wave function is closer to the interface. And that's why your mobility decrease. You have more surface scattering. Or maybe let me just call it interface scattering. My analogy is not good, but I do want to try to guide you to think that when it's narrow, you start feel the effect of the wall. Just like here, when this narrow, the electron feel the effect of the wall. So now it feel both the top and the bottom interface. That's why it goes down. Is that okay?
Professor, but based on that equation of the mobility of velocity divided by the, oh, that's electric field, it's not energy, right?
That's electric field, yes.
Okay, so when the electron is scattering due to the small confining of the barriers, it is losing energy. So the relationship that I'm getting based on that logic or that analogy is that the mobility is inverse proportional to the energy of the electron.
No, this is E, right? Electric field, not energy.
Oh no, I'm not talking about that equation because you're saying that the electron is scattering through those barriers, right?
Yeah.
And then when the electron scatters, doesn't it lose some energy? And that would make the velocity, the mobility to go up?
No, you lose energy. It means you when you hit the barrier, right? You lose energy. It means you keep losing energy, so you cannot have a high mobility.
But on the graph, it goes high.
Huh?
But on the graph, it says that the mobility goes high during that.
Only here. In this range, it goes high because first you have less intervalley scattering. But then when you go even narrower, it becomes very small because now you have a lot of interface scattering.
Okay. Yeah. I was moving in the wrong direction. Okay.
Okay, great. So you have two mechanisms. Yeah, so they are competing. Good. Any questions? Now, if not, then let's go to self-heating. Someone asked this a week ago in Piazza, and now eventually we reach here. So what is the problem of SOI? The problem is that the thermal conductivity of oxide is very low. Silicon is 148 watt per millikelvin. This is thermal conductivity. It's telling you how fast they can transfer the heat, right? You know about thermal conductivity. In the kitchen, the metal has very high thermal conductivity. It can dissipate the heat very fast, cool down whatever inside, right? And if you have a silicon, means glass, right? You have low thermal conductivity. It keep the temperature inside for a long time, right? So now the problem is, now we have this box inside, which has a low thermal conductivity. For thermal conductivity, sometimes we call it kappa, okay? Right, this is a small kth, okay, or kappa. So your heat cannot go away. Okay, I can, probably you know already, but why there's a heat? Why there's heat in the body? Why? In your transistor, why does it heat up? A very simple question, but I hope that you can get the right keyword. Why the transistor get hot?
The electrons, thermal heat.
Just Joule heating, thermal heat. You have current, you have voltage, Joule heating, right? So in this region, you have a lot of Joule heating. On FH, V times I, IV. That's it. Higher temperature, higher voltage, higher current, more heating. Once you heat it, you just like you boiling it. The temperature goes up, then you need to dissipate the heat. Okay, so here shows the problem if you use SOI, right? So this is the bulk. When we try to increase the device power, which is VI or IV, right? Then temperature goes up. Channel temperature. This is the channel temperature here, right? Wow. If you use SOI with very thin silicon, you see that it can go up by 100, go to 140 degrees C. Well, that's a lot of problem, right? Heating, the major problem is reliability. Many things, they last for a long time at low temperature. But if you heat it up, because of the so-called Arrhenius pot, right? You know, reliability, many things, right? Reliability basically is like reaction. They proportional to the exponent of activation energy divided by kT. Once your temperature go up, many things will happen. Some of them originally take 1 billion years to happen, but now you can take 1 year to break down. Okay, so that is the problem for SOI. So this is something you want to memorize. Any questions? You always remember SOI has this problem, okay? But of course, we can try to solve it.
So what's done to mitigate it?
Mitigation, basically you cannot, but people will start thinking, can I make the box thinner? And then can I, for example, thin down the substrate and add some more cooling? Yeah, but if you have the same thickness of bulk versus SOI, you do get higher heating, more heating in the SOI. Okay. Now I want to talk about impact ionization. We learn about the, maybe let me just ask you this one. I draw the Venn diagram again. You're very familiar with this Venn diagram, right? So this is negative. Can you tell me on the right, I already told you, on the right, what bias do I apply? Is it positive? This is a PN junction, right? Maybe on the left, what type of material is that? Is that N type or P type? On the left. P type. Thank you. Because the Fermi level is low, right? So this is given. So on the right is N type. So on the left, do I have a positive or negative bias?
Negative.
Negative bias.
Thank you, because it go out, right, on the left. So on the right, it is positive, right? I hope that you can do this easily now, right? If you cannot draw this, basically you cannot do any assignment. Okay, so we learn about diode, there's no current. Why? Because now I have negative. Of course, it will try to drive the electron to here, but I don't have electron in the P type, right? Very few electron at the P type. And here, positive is here, right? I try to push the hole to here, but I also have very few holes, right? So that's why you have low leakage current, very low. But of course you say, hey, last time we learned about band-to-band tunneling, remember? Can someone describe to me what is band-to-band tunneling again?
It's when the depletion width of the junction is very small, that the electron goes to the barrier due to the quantum mechanics mechanism.
When it is very small, then go to tunneling. Where to where? Can you say it?
Valence to conduction band.
Valence to conduction. Good. So we have something like this, right? Then this is called band-to-band tunneling, right? Not related to this topic, okay? So we have the current, because then the electron can go down, hole will go up. So now what I'm to say about is something called impact ionization. So that is what happened. Oh, you do have very tiny electron. Okay, good. Then the electron travel, right? Not much. If the travel, think about if this is the cliff, and you jump, you run, you drive the car, go out the cliff, and if you don't fall, isn't that you have a lot of energy compared to the fall of the ocean, the surface of the ocean? Okay. Now suddenly something happened, you fall. What happened to this energy? Your energy, if it is larger than the band gap, you hit the lattice. You hit the electron that are bind to the lattice. And because of this, 1, 2, what will happen? You are going to, so I need to redraw it because it will be difficult to see in the future, right? 2, you become here, then you are the electron here. I lose all the energy, but where does the energy go? The energy is going to create from here a hole and then electron, right? I get your energy and then create an electron hole pair. Oh, good, I have hole now. And then I have electron, right? Do you see that? But what happened to this hole? Well, the hole under this electric field, maybe I should not draw in this way, it will continue to transport. I think I can use red. And then suddenly, again, it hit by another particle. Not hit by, suddenly it loses the energy by hitting the lattice. Then what happened again? It's going to create another hole and then another electron. I get another electron. Then what will happen? It will travel again.
Are those electrons tunneling? Is that what's going on there?
So here vertically, we don't call it tunneling. You can say tunneling in a certain content. It's also okay to say tunnel to a higher energy, but actually it's in the same location. It's just that you have, for example, you have a phosphorus, right? And then you not need to be phosphorus. Let's say you have silicon, you bond to silicon, right? So you have 2 electrons in each bond. Okay, and now you have a very energetic particle, which is the red, right? The red goes in, come here, and then it lock off my electron. This one becomes a electron and then a hole, just like this, but they are at the same location. You see what I mean? A very ordered lattice, I have a ball comes in and knock off the ball, then the vacancy, or in the classroom, right? You guys sit on the chair, some people come in, knock off that guy, and then you become a moving person, electron, and then you have an empty chair. With this empty chair, other people can start moving to your, and it becomes the hole. So you have hole and electron created at the same time. This is nice step 5 and 6. Is that clear? Do I answer your question?
And so the electrons move up to the conduction band because they're free at this point?
Because they gain the energy. You just think that this is energy, right? This direction is energy. You think of that, you were living on the 2nd floor. Now some people knock on you and you gain all the energy. You went to the 5th floor. And then your 2nd floor room becomes empty and you are on the 5th floor.
Okay, that makes sense. Thanks.
Okay, so basically here you can see one electron go up. So what does it mean? Then you just repeat. That's called impact ionization. And this is also what we call avalanche breakdown. It's just like the snowball. You start with a very tiny snowball here. Because it gains enough energy, it generates other smaller snowball. Then you keep rolling, then you get a lot of hole and electron. Electron travel here, create another pair. Hole travel here, create another pair. As long as each time you create more than one pair, then you have this multiplication effect. For example, I come here, I create 2 pair, then I have 2 hole. The 2 hole come here, create 4 pair. I have 4 electron. 4 electron come here, create 8 pair. I have 8 hole. 16, 32, it go up very fast, million, billion, and then your diode break down.
So what does this cause? I guess what's the macro effect that this produces?
The macro effect, if you want to look at like classically, you really can think in this way. One single electron comes in, right? Let's say you have very few electrons, your silicon is not conducting. It comes in, but because of the high electric field, it does not lose the energy. It keeps gaining energy. Eventually, suddenly, it hit one of the electron. Then it becomes the electron hole pair. Then this hole is going to travel back. And this hole is going to eventually gain enough energy, hit another pair of electron. Then the electron will travel back, right? But if you actually the hole generate 2 pairs of electron, right? Before you lose the energy, you gain enough energy to generate 2 electrons. Then you have 2 electrons coming here. Then these 2 electrons generate 4 hole. Then hole will go back. Just keep iterating. From a classical perspective. Make sense?
Does that degrade the material or cause it?
Yeah, very good. Does that degrade the material, right? The good thing is for impact ionization, when you have a lot of current you heat up, it may degrade your material. But if you control it so it doesn't have so-called thermal runaway, it won't. Because remember, it's not changing your atom. The energy is not high enough to move the atom. Your atom is still there. You only knock off the electron. Knocking off electron is not a big deal, right? Electron move, and then once you go to steady state, electron will fill up the hole again. Basically, just like saying that you see in the classroom, someone coming to knock you off. If your chair is fixed to the floor, as long as the energy is not large enough to move your chair, even you guys moving around, locking around, later you leave the classroom is still intact, right? Just like this.
So at the end of step number 5,
Yeah.
are we left with 2 holes?
Oh, yes. Well, at step number 5, the hole becomes a smaller energy, right? So if I should also draw a hole here, you're left with 2 holes, yes.
So this is essentially how a Zener works, right? A Zener diode.
Exactly. This is just the Zener diode. Right? So for Zener diode, you don't worry that it going to degrade your diode. Of course, you cannot go too high the voltage because it have the heating effect. Right? If they don't have heating effect, impact ionization is good. It's no problem. Okay. Any questions? Now, if not, let I introduce concept because I need to talk about the Kink effect in the SOI. Okay, so what is the Kink effect? We measure the ID, right? This is ID, this is VD. So suddenly it comes up when the VD is high enough. Why is that? Because SOI is like this. But this is for partially depleted SOI. So here you have the depletion region, right? When you go to let's say 5 volts VD, what happened to this junction? It is reverse bias. So when it is high enough, you have impact ionization. Right? Yeah, all of your physics you are interested and you care happen here. I only care about the current. But unfortunately, at the same time, you have something going on here. NP, impact ionization. Well, that happened to bulk also. But the problem is in SOI, this is floating. Right? What does it mean? It's not connected to voltage source. My writings. In SOI, right? Remember, we don't have the body contact, no body contact. So let's come back to here. For the P, we get a lot of hole, right? During the impact ionization. So a lot of hole. Then you get a lot of hole. Accumulate. They have nowhere to go. Then you increase the potential. You actually have a positive VB. Remember, it's just like you apply positive bias to the body, and this will give us lower VTH. Remember, just like body effect, right? So because of the impact ionization, I create a lot of hole here in the bulk. Well, you just go to the substrate, so no accumulation of hole. Here you keep accumulating the hole, and then you lower the threshold voltage. That's why it goes up. That is what we talk about, Kink effect, right? So someone asked about something similar to this before in the piazza. Is that clear? Now, but this has some good effect. People try to harvest this effect to have less than 60 millivolt per decade subthreshold slope. Okay, and PMOS is less susceptible to this because it's more difficult for hole to initiate the impact ionization. Okay, so here is the Kink effect again on the left, right? So this one is here show that when it is partially depleted, right? We look at this potential well, the hole comes in, right? This is the quantum well, this is the conduction band, the hole comes in, and then the potential. Sorry, this is not the conduction band. This is just the potential, right? So this is 0 volt. This is 5 volt. Okay, the hole will accumulate because of the impact ionization. The hole accumulate. When they accumulate, then you bring up the potential. Okay, as a result, you reduce the threshold voltage. So what is the solution? You can make it fully depleted. Okay, if you make it fully depleted, then this hole will be drifted away because there's an electric field. The problem is because of this neutral region. Okay, so I'm done with SOI, right? Any question? I spent quite a lot of time, but they are applicable to FinFET. That's why I'm slower than what I'm supposed to be. Any questions? If not, let's go to